Hello and welcome to the wolfSSL live webinar, Secure and Reliable Firmware Update with wolfBoot, presented by wolfSSL Senior Software Engineer Daniela. My name is Shizuka and I will be moderating the webinar. All attendees will be in listen-only mode. If you have a question, please use the Q&A box. We will host a Q&A session following the presentation. The webinar will also be recorded and made available on our YouTube channel shortly after the presentation. I invite you to follow us on Twitter at wolfSSL, as well as our other socials. Also, feel free to email us if you have any additional questions. And now I would like to give a brief company overview before we move to the technical presentation. Today, wolfSSL secure over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of over 50 dedicated employees, most of which are engineers. This progress is of course supported by a strong partner network that we are proud of. Since the beginning, our engineering team has developed several embedded security products, including WolfClip with DO-178 support, HIP certification, and HIP's ready offering, MQTT up to the V5 specification, SS8V2, TPM 2.0, a secure bootloader known as wolfBoot, as well as Java wrappers and JSSC support, and commercial support for Coral. All of these offerings are accompanied by through maintenance and support plans up to the 24/7 level. We also offer full service consulting. And now I would like to turn it over to Daniela to talk about secure and reliable firmware update with wolfBoot.
Thank you, Shizuka. So, hello everyone and welcome to this webinar. Today we're going to talk about secure boot, and we start from the motivation, of course, that brought us here. We've been in the field of IoT security for since the beginning. As Shizuka was mentioning, the company has been around since 2004, so for about 20 years now. So we know the problematics that are linked to keeping your devices safe. And this, of course, includes keeping your connected device updated, and which means that you always may expect some kind of flaws that might come up, or vulnerabilities that can be discovered at any time that might affect your device, both from your side when you're developing a product, but also from all the components that you are going to use, including, for instance, TCP/IP stack, or even a TLS stack that we would provide to you, for instance, wolfSSL. And you know, vulnerability management is a dynamic problematic, so we need to keep our device updated, because vulnerabilities tend to move very fast, and updates must be available in the field, and they must be delivered in a secure way and as quickly as possible. As wolfSSL, we commit to our approach, which is reacting to vulnerabilities that can be fixed within 24-36 hours from the report, when we immediately release a new version. And it's in most cases, this means that the fix is available long before the vulnerability has been disclosed to the public. What this means is that we need to have a way to update our firmware or our software on our devices. And the first questions we asked ourselves when we started this project was, is there a standard way to implement firmware updates? Now, at the time when we started the project, there actually wasn't one, but there was a group within the International Engineering Task Force called SUIT, which is an acronym for Software Update for the Internet of Things. And this group was working on an internet draft at the time that later on became an RFC 1919. This proposed standard was, in fact, foreseeing that the presence of a secure bootloader, and the secure bootloader should be agnostic on the way the firmware is actually transferred to the device, and it needs to have specific characteristics, such as, for instance, having a small parser, because those are the software components in a secure bootloader that are expose the largest attack surface in literature. So, and most important thing, the bootloader should provide a secure mechanism that is based on asymmetric cryptography, so on public key mechanisms, to verify the authenticity of the firmware, and of course a way also to verify the integrity of the firmware that has been transferred to the device. So based on this, we decided to do that. So writing a secure bootloader. It took a long time, especially to cover all the corner cases of dealing with secure boot and secure firmware updates. And of course, this includes the reliability and security of the update mechanism, code safety, and testing all the corner cases, as I was mentioning, and all of the issues related to key management, key creation, key distribution, etc. And as we will see, there are additional requirements related to the way we handle these keys in the device, and how the key management is done within the device. So the chain of trust, trust anchors, and the relationship with the secure elements that might be in place. And for this reason, we strongly suggest you not to attempt the same exercise if this is not the focus, the main focus of your project. So the same way you wouldn't write your own TLS library or TCP/IP stack most of the time, or your RTOS kernel from scratch for your embedded project, you should also consider using a well-tested solution for your secure boot. So that's why we figured there was a need for a universal secure bootloader. And our additional goals that we posed on ourselves include the portability across initially all 32-bit microcontrollers, then later on all 32-bit systems, including CPU-based, and then nowadays we support much more than that, as we will see. For this reason, of course, we want to use standards such as SHA-2 or SHA-3 digest mechanism to verify the integrity of the system by comparing the hashes. And of course, the mandated public key-based firmware authentication we were talking about, coming from the RFC 1919. We also wanted it to be as small as possible, to fit into the smallest microcontrollers on the market. And we also decided to make it memory safe from the beginning. So disallowing any type of dynamic memory allocation in order to make it not just secure, but also very safe. And this has been an advantage later on. We'll mention this while talking about certifications. And of course, as RFC 1919 suggests, we should be independent from the way the firmware is transferred to the device. And we also decided to make a mechanism that provides a fallback for an authentic image, but that has a bug that might fail to boot your device. So we do want a mechanism that fallbacks to the previous working version and avoids kind of things like breaking your device, especially if it's difficult to reach physically on the field. So that's how we created wolfBoot. That's what we're talking about today. wolfBoot is the open source universal secure bootloader for you. It's designed for the IoT. As you may imagine, we started the development from small microcontrollers. But nowadays we support most of the common architectures on the market, including PC-like embedded system running Intel x86 32 and 64-bit, and of course RISC-V and PowerPC on the side of ARM, and also since the latest versions also Renesas RX devices. So the features are what we already said, plus it's OS agnostic, so it integrates with any bare metal program as well as real-time OS or operating system solutions. Provides support for kernel and rootfs updates in embedded Linux. It's more flexible than that. We would see more of this later. We do have a very flexible chain of trust integration. So we can work as a standalone bootloader, integrating an existing secure boot chain, and can even be compiled as a library to equip an existing bootloader that is not a non-secure bootloader with secure boot functionalities. Firmware authentication is done at boot time. This means that every time you boot up to your device, there will be a public key verification of the authenticity of the firmware itself. We do support many types of secure elements and crypto hardware accelerators. We support directly TPM 2.0 devices. We have the mandated small and safe parser with no dynamic memory allocation, as I was mentioning. And we do also have encryption for external storage that don't require execution in place. wolfBoot is capable of receiving and handling self-updates, so update itself. There is an easy key management and provisioning system that can be integrated with any existing key provisioning infrastructure, even if it's provided by third party, or can be completely integrated in one single machine that's capable of, at that point, of signing any firmware where you use your private key to sign the firmware. And of course, like all our products, it is actively supported and maintained. The entire wolfSSL team is working full-time on new features, bug fixes, improvements. There are, as for most of our products, at least 4 releases every year. That's our target. And we provide support packages up to 24/7 for life-critical projects. It is very portable because we have a hardware abstraction layer that reduces the target-specific code to the minimum. And we do support external flash as just like a SPI or any non-volatile memory that's storing the partitions containing the firmware or other data that you want to authenticate and verify for integrity. As many of our products, as all of our products, the source code is available, including firmware update examples under the GPL license on GitHub. And we can provide, of course, commercial licenses that don't include copyleft for integration with your proprietary projects. How does key management work? The key pair is generated once on a specific machine. The private key stays on this server or developer machine, and it's never shared with anyone. It never goes in the field. The public key, on the other hand, must be stored on the target and must be accessible to the bootloader. We will see there are several ways of doing this. There is no revocation mechanism provided by default, except for bootloader updates, or if you are storing your keys in an encrypted bag on the device, and you include that encrypted key store among the components that can be updated through a firmware update. And then after the key is created, this key pair is created, a sign tool will be used to attach manifest header, what we call a manifest header, to the image. This manifest header is used to validate the integrity and authenticity of the image. It contains a number of metadata about the firmware itself, including the signature, the SHA, the key that's used for the public key that should be used for verifying the firmware itself, the version, and this is very important because the version is part of the verified payload and it cannot be altered without actually compromising the validity of the signature of the firmware itself. The only thing that wolfBoot relies on from the hardware point of view is the presence of a trust anchor, which is specific type of root of trust, which consists in public keys that are used to verify the signature. A trust anchor, that's also defined by RFC, is basically just a public key and its associated data. That can be used for verifying digital signature. The requirement for the trust anchor is that it has to be stored in the device and can be also more than one, of course, and each one can have its own role. The requirement for secure bootloader regarding trust anchor store is that the trust anchor store must resist modification. So it means that it needs to be write protected. This can be done in different ways. For instance, on microcontrollers, it is usual to see flash readout protection, which also includes write protection. So there is no harm if your attacker reads your public key, of course, because that's public by definition, but it needs to be protected for writing. So it should not be possible to overwrite the trust anchor. But sometimes a flash protection itself is not secure enough, especially on those devices that are reported to be to have a compromised write protection on the flash, for instance, due to glitch attacks, etc. So depending on the level of security that you want to reach in your project, we suggest that the trust anchor store could also be implemented using secure elements and even using a separate third-party trust supervision authority so maybe also provided by the chip manufacturer itself that can may install trust anchor that are specific for your device in your production line. So just to recap how the key management work, we generate the key pair just once. The private key, as we said, is left on the server on the development side, and then the public key is then loaded in the device, so it's accessible by wolfBoot. wolfBoot then will use the public key to authenticate the firmware itself. How the firmware is signed, you have to provide the unsigned firmware and its version number, and of course the private key, and these three elements using the sign tool will produce the signed firmware. And the signed firmware will have that manifest header at the beginning, which is a fixed size. It can be 256, 512, or 1 kilobyte, depending on the algorithms that we decide to use there. And then the authenticated firmware that's signed will be then authenticated by wolfBoot using the public key. And then at that point, the device is allowed to boot that firmware. And of course, this also happens every time your device receives an update, as we will see. We talked about algorithms. wolfBoot can be configured to use any of the algorithms available from wolfcrypt, which means ECC up to ECC 521, RSA up to RSA 4K, ED25519, ED448, and since the latest version, wolfBoot is also supporting post-quantum algorithms, namely LMS and XMSS. To our knowledge, we are the first secure bootloader that supports post-quantum cryptography on embedded devices. So what happens when you receive an update? Of course, there are two possible strategies there, and that depends mostly on the restriction of your device is bringing, because All types of IoT devices can usually access a boot update approach where the active firmware is always booted from the same physical address. And then this, of course, requires a swapping between the boot and the update partition when a new firmware is available to be considered for verification and potentially for installation. On other devices that have virtual memory management engine, such as CPU-based devices, in that case, we also provide the AB approach for position-independent firmware. So you can just map your memory wherever you want. So you do have two partitions that are, in fact, equivalent. You can use one for booting the current version, and the one that's not in use is used to receive the new firmware update. And of course, this is not recommended. This second mechanism is not recommended for position-independent firmware images because microcontrollers have restriction on the fixed address where the firmware must start. And of course, it does not allow to use external MVMs to execute code on external MVMs. So in the simplest case for microcontroller-based device with small flash, everything on the same partition, on the same flash devices, that's all executable in place. You get this very small partition that contains the bootloader, the beginning of the flash space, then a boot and update partition that are usually the same size. The first one is used for actually booting the firmware, and the second one is used for receiving the update. And then you have a swap partition that's as big as a single page that you can allocate on your flash memory. Sorry, a single physical sector size, so that when we are swapping the two images, there's always two copies of the same sector. So the update can be interrupted at any time, and wolfBoot will be able to resume that. So we'll see. And of course, in this case, update and swap partitions can be freely mapped to an external MVM, such as an SPI flash or any device that can store data permanently. And in that case, we also support, as mentioned, encryption using a symmetric key that can be negotiated, derived, or sent through a secure channel together with the updates or in two different moments. In the AB mechanism, could be a CPU with VMM, but also some microcontrollers support a single registry flag that swap the two partitions in place, like some STM32 devices do this, a few microchip devices have an option, a similar option. So this means that even if you cannot, you don't have virtual memory mapping, by flipping a single bit, you can swap the addressing of two separate banks on flash device. And but in any of those cases, CPU with VMM or hardware system memory swap, the two partitions are equivalent basically. And at the startup, the bootloader will run an election on the image with the greater version that's been activated. So it verifies the signature and stages that image. And if the signature is not valid, it will fall back to the other partition and repeat the operation. Every time we do an update, in both cases, both A and B mechanism and the boot update mechanism, a copy of the previously running image is kept in the other partition until a successful boot is confirmed. And of course, partition can be mapped by a previous boot stage in the case of a chain loading architecture. So the typical use case on microcontroller devices is boot update swap, as we've seen, on the same flash. But of course, it can also be boot on the execute in place partition and then update and swap on a secondary flash. for instance, SPI. And when hardware-assisted swap is supported, as mentioned, boot and update on a exip flash and duplicate the wolfBoot. Sorry, A and B on exip flash. This slide is wrong. And duplicate the wolfBoot. On CPU-based system, we do the A/B. We can do separate stages to initialize systems on more complex system like x86 when you have to change architecture while you're booting, and it's more complex to keep everything in one single bootloader. So we do multiple stages there to organize the boot staging. And in that case, of course, the stage one bootloader, the stage one wolfBoot will be responsible for verifying the authenticity of the stage two wolfBoot. And you can also update stage two wolfBoot from stage one, etc. A/B partition election is done at boot. Usually the bootloader is on a different NVM. For instance, it can be on its separate ROM, while your Linux image is on a SATA disk, for instance. And typically you have multiple images to verify. For instance, Linux kernel, rootfs, and whatever it's immutable on the system that you want to ensure that's not being tampered with by a potential attacker. And of course, there is an advanced interaction with other boot stages, also using different standards like multi-boot and even EFI. The specific characteristic of that we support for hardware-assisted bootloading on microcontroller devices, we support hardware acceleration on several HSMs. We do support, of course, as I said, integration with TPM devices. We have a support for TrustZone M on RV8 M, where wolfcrypt stays active in the secure domain and provides this PKCS11 engine that can be called by non-secure applications to access crypto functions while it's running. So it's a little bit more than just bootloader in that case. We can talk about something similar to TrustZone Manager, which also provides a way to hypervise the access to specific crypto functionalities and its own secure vault that's needed to store private keys and secret material from your application can be protected via the hardware separation that's provided by TrustZone M. On CPU-based system, we have support for Intel BootGuard, provides reliable hardware-assisted root of trust, and contributes to the measure boot mechanism to ensure that the hardware has not been modified during the in-between boots. And we're working on support for TrustZone A in a similar fashion to the TrustZone M, where we can act also as a hypervisor, again, to provide crypto functionalities without having your software accessing directly from memory secrets like private keys and symmetric keys that have been negotiated. Other advanced feature we have, we do support Delta updates, which is pretty useful in some use cases, especially for bandwidth impact on receiving updates or size on the non-volatile memories to store an update. So the mechanism here is that we create a binary patch between two versions, which is usually much smaller than transferring an entire firmware, especially if you do update often. So it just you just have to transfer the difference between the two binary images. And in this case, we do provide two levels of authentication, because first we verify the authenticity of the patch we received, then we apply the patch, and then we run the usual authentication test on the patched firmware. That's in this case is going to be the newer version, and it's also possible to still keep a version of the image available, of the last known working image available, by implementing a revert. That we do implement this revert through thanks to the fact that we actually send a two-way patch. So a patch, it's actually two patches from going from version A to version B and vice versa from version B to version A in case we need to fall back to a known working image. Something else that's quite unique in the world of secure bootloaders is channel and glitch attack mitigation. We do provide a protection against voltage, clock fault injection, but also against electromagnetic fault injection, which are usually external to the device because they are based on the principle of let's say, irradiating the device with specific very strong electromagnetic interference until the device itself actually skips an instruction. And we did implement architecture-specific countermeasures for this that consists mostly in volatile inline ARM assembly that allows us to repeat the checks or check canaries, for instance, to ensure that the authentication is actually run before accepting the validity the validity of the authenticity check. Other things we already mentioned, we support external HSMs for signing the binaries, but also for storing trust anchor. We do have seamless integration with third-party provisioning mechanisms for HSMs, like network HSMs that sign your binaries for you. For instance, if you don't own your own private key because it's handled by someone else, by your supplier of this kind of services, we do have a seamless integration mechanism in our signing tool that allows that step to be offloaded to an external process. We already mentioned wolfBoot can update itself, and we do support multiple partitions with multiple public keys. So we do support now up to 15 custom partitions, and each key can be configured through a permission mask, so that you can, for instance, use one key just to update the bootloader, one key to update the main image, and a different key that can update only the application side data, for instance, that's on a separate partition. And you can, of course, have a key that can authenticate all of them by just setting a mask to all Fs. The integration with wolfTPM has been improved, especially in the last few months, and wolfBoot now integrates with the wolfTPM, which is our very own driver to access all the functionalities from TPM 2.0 devices. So we could already offload crypto operations to the TPM's hardware accelerator, so replace our software implementation with the hardware accelerated version of the same algorithm that's running on the TPM itself. We can use TPM as a trust anchor to store the public key, and we can also implement mesh boot using PCRs, and we can lock secrets into the TPM non-volatile memory. It can be unlocked then by reproducing a PCR policy and proving that the verification can be done using the keys during boot time. So this is an example lifecycle with wolfBoot that provides security mode firmware updates on an embedded device. So when you start your development in the factory, you want to, of course, flash wolfBoot probably through your JTAG or SWD interface, and then at that point, you also want your initial firmware, and of course, even the factory firmware, the version 1, needs to be signed with your private key that we created before, of course, deploying wolfBoot with its own public key in it. So this factory firmware will be in the boot partition in this case, and then you can just ship your device to the field, because at this point you can also get rid of the JTAG, for instance, or enable your write protection on the flash. So the wolfBoot and the current firmware will be sitting there. The device will be starting normally. wolfBoot will verify and stage the current firmware image on a normal condition, and every time the device will boot up, of course, there will be an authentication verification for that the current firmware is still valid and we can boot up. At this point, we are ready to receive a firmware update through, for instance, over the air, still signed with the same procedure. And wolfBoot will verify the update at the next reboot and check that the new image is actually newer. That prevents the rollback attacks, verifies that the integrity of the firmware using SHA-256 or SHA-384, SHA-3, and then verifies the authenticity of the signature exactly as it happened for the boot firmware. If everything goes as expected, then we're ready to swap the two images. So the update will now sit in the boot image, and the previous known working firmware, in this case, it will be your factory firmware, will be moved to the update partition. So it is possible, if something goes wrong, to revert that. So at the next boot up, everything remains normal. So wolfBoot will stage the current firmware, this is now version 2, for instance, and from this moment on, if you confirm that the current firmware is properly running, the update partition is free again to receive the next update. And if this fails, of course, we are going to switch back and fall back to the previous version. Swap operations are a big concern for some of our customers, especially those that send items into space, because they don't want to break their device. And if there is a power failure, you don't want your microcontroller to become a brick. And so power can be interrupted at any point during the swap operation. It's the most delicate operation. And because wolfBoot keeps track of the completed step, and as I said earlier, it keeps 2 copies of the same sector at all times. So swap operations are in general fail-safe. The only exception to this is the self-update for the bootloader itself, which is not considered fail-safe, power fail-safe. So it should only be used as an emergency. For instance, if you decided to include your trust anchor in the wolfBoot image, and you want to revoke your key because your private key has been compromised on your computer. Now, this covers more or less the secure boot part. I want to spend a few words also on what comes next. So it's secure firmware updates and what are the best practices, what we see often in the field from our wolfBoot users, and what are some of the possibilities to implement secure firmware updates, since the bootloader itself, as we said, is transport agnostic. These are the problems that are solved by the bootloader itself. So we provide the secure and reliable firmware update mechanism, key management tools, detect and discard corrupted updates, non-authentic updates, manage interaction with hardware accelerator, clear text or encrypted external storage, etc. What we don't do is prevent firmware updates to be intercepted. Of course, this is less of a problem if you send a new update because all their eavesdropped and intercepted images are not valid anymore. Once you send version 3, the device won't accept version 2 or 1 anymore. And of course, ensure that only authorized device can receive the updates, because this is not the goal of the bootloader itself. So you need some kind of secure protocols in order to transfer your image to cope with this additional requirement. So there are a few protocols that are preferred in the IoT market, and then just a second. My screen is okay. Sorry, technical problem for a second. Major cloud services as well as backend infrastructure can use any standard protocol and technologies for secure communication specifically for IoT devices. Protocols that are based on TLS 1.3, for instance. 1.3 is the latest version recommended by ATF. wolfSSL offers TLS 1.3 communication, so you can directly use those sockets to transfer your image. And we can also do that in an OS agnostic way, and it can be adapted to any transport or data link infrastructure that exist already. So even custom, unique machine-to-machine communication scenarios, non-standard transport protocol, etc. But we do provide an entire ecosystem of tools for communicating and securing data in transport. So it's we can access, let's say, different types of technologies. That's on the bottom cloud there. So that's all the data link communication protocols. You can have a custom transport layer as well as TCP/IP stack, and on top of that, we offer a wide range of tools that will enable single protocols that can be used on top of this infrastructure, such as MQTT, as we will see, and others. The three of the most popular solutions to synchronize and update firmware are often HTTPS, SSH through SFTP, and MQTT over TLS. And this is because they are standard protocol. They're easy to integrate with cloud services, especially, but also with your internal infrastructure. And they provide the best encryption and client authentication solutions. So you're solving the other two problems. So eavesdropping, so intercepting a clear text image while it's being transferred, and also providing an authentication mechanism for the client side, so for the device to be authenticated in your infrastructure to receive the updates. So just look at it one by one. SSH is the Unix way, we said. So it's the most popular system to transfer files among Unix system administrators. SSH doesn't only provide, of course, two-way authentication between the endpoints, but it does offer abstractions for secure file transfer. There is secure copy, which we support in wolfSSH, and there is secure file SSH file transfer protocol, SFTP. In both cases, we provide custom callbacks to implement file transfer abstractions, even on those targets like microcontrollers that don't have an actual file system. So you can map a specific file name to be your update partition, for instance. And it's compatible with everything that supports SSH 2.0. So wolfSSH is one of those solutions. One of the most popular products, open source projects out there is curl, which give you secure access to web services. What? Okay, sorry. And sorry, I'm having technical problem with Zoom. Sorry, okay. So curl is, of course, the Swiss Army knife tool for accessing, as used as a client for many protocols. So very popular when used as a HTTPS. And we do also provide a HTTPS client in the form of TinyCurl, which is a HTTPS 1.0 only library, which is usually under 100 kilobytes for deployment on a 32-bit microcontrollers. And the typical scenario here is you access some web server and web servers that run over HTTPS, and can also so curl can access, of course, both file transfers through GET and POST, but also REST services that are exposed on your cloud server. And last but not least, of course, MQTT. MQTT is the most popular messaging protocol out there, supported also by most cloud providers. And wolfMQTT is our client-side solution that supports by default MQTT over TLS, so encrypted and authenticated again. And it's on port 883 instead of 183. And it's easily integrated on all RTOS and bare metal applications. And it is, again, very popular in cloud providers. And we do support up to the latest standards, which is MQTT 5.0, and even MQTT-SN, which is running on top of DTLS or UDP instead of TCP. And this is mostly for the network lag that includes radio devices, lightweight radio devices that don't have enough resources for TCP or are running, for instance, on a mesh network and don't need the reliability of TCP and TLS. So MQTT-SN is in fact stands for sensor network. So it's really designed for those mesh targets. So in conclusion, secure boot and remote firmware updates are a requirement for IoT, and not only. We see this also more and more popular on, for instance, end user devices or all devices that might be accessed physically by a potential attacker. And wolfBoot alone implements a secure boot as mandated by RFC 1919 through the public key authentication and also provide the support for a reliable update installation mechanism that does not depend explicitly on the transport. wolfSSL is the library that brings TLS security to AIT world. So it means that you can install wolfSSL on a small microcontroller device and still has all the features of an actual standard TLS up to TLS 1.3 and also DTLS 1.3 as it happens for the rest of the IT world. And then as we have quickly seen 3 possible solutions to use in combination with this. It's wolfSSH, curl or tiny curl, and wolfMQTT. And those offer the best available solution for uploading secure firmware updates in the field using standard protocols and very robust and widely tested mechanisms. And for more questions, of course, you can always contact us at support@wolfSSL.com. And now I think we can go through the Q&A.
Yes, so there's a question. Does wolfBoot support STM32F437 plus STM32F439 and STM32H573 and an STM32H753?
I would say yes to all of this. Let's say STM32F4 in general's family has been our first target back when we started the project, and it's still probably the most used one on and in our nightly testing continuous integration. So that's and there's quite a few customers on the field using it. The H7 is more recent, but we do support that as well. And yeah, we do have a partnership with ST, so we tend to include support for all microcontrollers from the STM32 family, including the SID0 and also the ARM v8M, such as the L5 or the U5 that support Trusted on M as well. So yes, the answer is with ST devices is it's quite easy, let's say, because that's one of the main targets that we support.
There's another question. How does GPLv2 affect embedded device if wolfBoot is used? Does it cause the application to be shared with others if the wolfBoot is used as a BIOS bootloader?
So what happens there is that wolfBoot is actually it has 2 parts. There's a bootloader itself, and there is a library that's called libwolfBoot that should be in the application that's used to communicate with the bootloader using usually some flags that we use in a non-volatile memory area that's not used by the firmware itself. So you will be actually linking this second library to your application to communicate with the wolfBoot itself. So yeah, it's still not, let's say, your application should still be GPL in that case. Of course, if this doesn't work with your project, we can always provide different types of licenses. Just contact your business director from your area.
There's another question. What are wolfBoot RAM and flash requirements when using STM32F4 H5H7 series MCUs?
That's an excellent question. So that depends mostly on the algorithms that we want to use. So usually we're talking about 8 kilobytes for LMS post-quantum algorithm, about 11 kilobytes for ED25519, and probably around 25 to 30 kilobytes when using ECC or RSA. But we tend to be within the 32 kilobytes of footprint for what concerns flash memory usage. For RAM, we fit. That's it. Because the fact is, probably 20 kilobytes of RAM are going to be used in the worst case scenario with the heaviest, or maybe 25 with the heaviest of our algorithms. But this RAM is made immediately available after staging. So if wolfBoot is not resident in memory, your application can still use the entire RAM area that's allocated for that. So it's just during the boot that we use the RAM, and then we get rid of that.
There is another question. It may come up in a later slide, but I am most interested in what advantage you offer versus using MCU boot with a signed package. For example, could you integrate with a TPM 2.0 on the target device?
I don't think we have enough time to enumerate all the advantages that wolfBoot has on MCU boot, but I will just try to. Yes, of course, the TPM 2.0 integration is one important aspect to consider. We do support specific HSM as well. We do have Delta updates. We do have an actual glitch protection mechanism that works. We are based on wolfcrypt, which is a FIPS 140-2 and soon 140-3 certified cryptography engine, and it's properly maintained and supported by expert team of engineers that are dedicated to that. And we are a company that focuses especially on those kind of technologies, while MCU boot is barely an open source project with a community of mostly volunteers that work on that. So, and embed TLS is definitely slow to react to vulnerabilities, and especially it's slow to implement newer technologies. We can make some bet on when we will see any post-quantum cryptography in the scenario of MCU boot, for instance. But I have a very long list. We can talk about footprint, we can talk about performance, we can talk about, best thing would be probably you should try and compare those. There are also some academic papers that talk about that.
There is another question: is wolfBoot intended as a bolt on to existing processing systems like an STM microcontroller, or is it available to device manufacturers to serve as the lowest level ORL and boot utility?
Excellent question. The answer there is both. We do have customers that are chip manufacturer that have implemented wolfBoot as their default bootloader and immutable being set in ROM. So in that case, there is no possibility of updating wolfBoot itself, because wolfBoot is set in stone in this ROM that's not available for access from the embedded engineers that are working on that target, but rather it's from the hardware manufacturer itself. But in most cases, of course, most of our customers have a custom device, and that's in most cases out of the box installation of wolfBoot will work. But in some cases, you want to customize that to have a more secure root of trust, or more partitions to verify more sets of key pairs that you want to use, etc. So it is very flexible, and it can scale up to replace BIOS also on an x86 computer, on a PC-like system. So we can replace the entire boot chain starting from the BIOS, basically, because we do have an integration as a slim bootloader, Intel Slim bootloader replacement, which uses the Intel firmware support package at a very early stage, so way before second stage bootloaders you used to, like U-boot or things like this. We can act actually at a BIOS level. The flexibility there, yeah, this just about what stages you want to use wolfBoot in, and how your boot chain is done, and then we can discuss any kind of scenarios there.
There's another question. Does wolfBoot take advantage of STM32H5 UROT IROT?
I'm pretty sure we're working on this one. We don't have a release of this yet, or there might be a pending pull request. But if it's yeah, this is coming soon.
Okay. Next question is what changes in respect to supporting Trustzone do you protect both application images of the rich and secure world?
Okay, so the scenario we have explored there is where wolfBoot is the owner of the secure domain. We have published a blog post about this. You should look for using wolfcrypt as a PKCS11 engine in Trustzone. So basically what happens that your application is going to be in non-secure domain. wolfBoot will act as a secure domain manager and will only open up the devices and memory spaces that are accessible for the non-secure world. And then everything else, everything that's related to cryptography at that point is in the secure domain. So you have your key storages in the Trustzone, and you have all the crypto running in the Trustzone secure domain. So wolfBoot in that case is just not just a bootloader, but it will stay there and wait for non-secure callable interaction from the application. So wolfBoot is the secure domain, your application is non-secure domain, and everything that can be accessed on the secure domain goes through the NSC through PKCS11 calls.
Another question is, does wolfBoot offer a method to transfer the image from cloud to the device and VM?
As I said, this is not the purpose of wolfBoot itself, as mandated by the RFC. The bootloader should not care about the mechanism to which the firmware is transferred. So it needs to be transport agnostic. So the answer in this case is no. And that's why we introduced also briefly wolfSSH, TinyCurl, and wolfMQTT as a few suggestions of what you can do to secure that part of the communication, just to have to ensure that your firmware image makes it to the update partition or through your B partition, for instance, and then wolfBoot will take care of authenticating and installing the images for you from there. The other reason why RFC 1919 prohibits to deal with the image transfer is because you would increase the attack surface of your bootloader. It would become something like U-boot, right? So it's a small operating system. It has a TCP/IP stack, and it has a huge attack surface, and that's not acceptable for most of our customers that need to implement secure boot. So it doesn't have to. It must not have an interaction with the outside world, because that, of course, increases the attack surface.
There's another question. Does the update service follow a specific standard like a CMS or TUF?
No, but you could implement those standards as a transport mechanism to, but not TUF. TUF, I believe this is specification related to the manifest header. So our manifest header might be different from that.
There's another question. When sending an image that has to be stored on external SPI flash, is the Canon image able to be loaded into SPI flash as a backup restore image?
Yes, and on top of that, if your update image has been encrypted and it's stored as encrypted, in the moment that two images are swapped, so your new image is moved to the boot partition and decrypted, the old working image that originally was in the boot image in boot partition will be encrypted before it's copied to the SPI. So this also prevents any wiretapping attacks on the SPI bus that could reveal your clear text image in both directions. So both when we are installing the update and also when we are storing back the current working image to the SPI image, to the SPI partition.
There's another question. Does wolfBoot require any code included in the application firmware to facilitate any part of the process? File upload to update region, or is this completely standalone, meaning to perform an upload for subsequent update? The application will need to jump to wolfBoot and then upload the new application code.
No, it's rather the former. So wolfBoot has a way to communicate with the application. Application, as I was saying earlier, has a little library that needs to set some bits in the flash. So it's basically the application has a few calls like start the update. There is a new update available, and that's good. I set it there. And the other one is okay, the last boot was successful. So you can mark a successful boot, for instance, at the point in your application when you know that the boot was successful and the device is reachable again from a remote location, and then that's where you call the success, and that's when wolfBoot knows that it can get rid of the last known working partition copy that is made in the update partition, and then free up the update partition again for receiving one. So yes, there is a little library that is used by the application that's completely portable, of course, across microcontrollers and CPU systems that signals to wolfBoot what's happening in the various steps of the update state machine. And there is no jump to wolfBoot. The only way to run wolfBoot is basically reboot the system and start from reset vectors.
There's another question. Does the bootloader work on RTOS platform? Will the wolfBoot support ThreadX?
Yes and yes. I mean, we are OS agnostic. The only thing that you have to change in your OS or system that's running on specific physical address, like in RTOS cases, is that you have to change your entry point. So to accommodate, let's say that you have a partition of 24 kilobytes to contain the bootloader, wolfBoot, and then your application will need to know that if it's linked physically to a execution in place, it needs to know that it starts from there. So you need to change the entry point of your application or your RTOS in the linker script file. For CPU systems, we do support most of the standards like multi-boot. We, of course, support Linux boot, so we support Linux and all the operating systems that use a standard to boot. And we do have also several different mechanisms, depending on the architecture, to map the PCI devices, do all the initialization and the bring up before handing it to the next stage. I'm not sure what ThreadX actually supports as a boot mechanism, but we do support multi-boot, which is usually the most popular mechanism among proprietary systems. Like, for instance, we do have several customers running wolfBoot with Integrity OS.
Okay. There is another question. Is ECC or RSA better PKI algorithm?
I'm not a cryptographer. I like both equally.
And it'll be the last question. Can you speak about your certification? I'm interested in integration into a medical device.
Yes, of course. Sorry, probably I skipped a little bit over that. We do have an ongoing certification process on the 0178C-A, which is the top certification, safety certification required for airborne devices. Okay, this is a different market, but just to give you a bit of a idea of how critical are the systems that are usually protected by wolfBoot. We have airborne wolfBoot already almost in the field. We are in the process of completing our D0178C-A certification. We do have customers in the medical devices area. Most of the times, this implies a few criteria in place from the process point of view, and especially on the unit test coverage point of view. So we have done the exercise with existing customers in the field of providing this kind of documentation and test results and artifacts and going through, let's say, it can't be an out-of-the-box certification, of course, because most of the times we're talking about custom systems and custom use cases, but we definitely are already on the field for medical devices that had strong FDA requirements. So we definitely need to have to assess this offline. So I would ask the author of this question to contact us so we can discuss exactly what this implies from the point of view of process and deliverables to get to the to reach the goal of having a secure boot on a medical device. It's probably we don't have enough time to discuss all the details in this webinar. Thank you for the question.
Okay. Thank you, Daniela, for hosting an informative webinar, and everyone for joining the webinar today. And please don't forget to follow us on Twitter at wolfSSL as well as at social. And also, if you still have a question, please email us at fax@wolfSSL.com. And thank you again, and see you next week.